Welcome back to the AutoML lecture series. In this part, we will talk about how to evaluate in neural architecture search. So, evaluating a single architecture requires actually full training from scratch, where the first works in that direction, or in NAS in general, from Sof and Lee from 2017, used up to 800 GPU hours to actually evaluate 20,000 architectures. And as we can see, this performance estimation strategy is the biggest practical bottleneck in NAS, since we do not want to evaluate and train 20,000 architectures. Therefore, cheaper estimates would allow the search strategy to explore far more architectures than only the 20,000 within the same budget. With the key question we want to answer within this part is, can we reliably predict which architecture will perform best without actually needing to train it fully to convergence? We will talk about the performance estimation strategy, which drives the search strategy within the search space A. So, there are different types of performance estimation strategy. On the one hand side, we have the evaluation for the ground truth accuracy, which early works in NAS actually did, but we can also use performance prediction methods, or so-called surrogate methods, which are based on two different parts. We have an architecture encoding as well as prediction model, which uses the architecture encoding as an input and then predicts the accuracy of the input architecture using, for example, a random forest or a multi-layer perceptron. We will talk about both of these things within this part. So let's talk about the ground truth again. Early stages of NAS actually did the evaluation for the ground truth performance, needing up to evaluating and training up to 20,000 architectures on Cypher 10 for image classification, using 800 GPU hours in order to be on par and a little bit better than the actual human-designed neural networks. Since then, the goal is to speed up the evaluation, since we want to efficiently find a high-performing neural architecture without the need of 800 GPU hours. And that's where so-called performance predictors come in. The definition of a performance predictor is based on having a search space A, an architecture small a within the search space, and the final validation accuracy C of A, after a full training pipeline P. So the full training pipeline involves the amount of epochs, the batch size, the learning rate, weight decades. And the validation accuracy is on the downstream task of interest of our architecture A. Within the search space, math call A, which we already described and talked about. And a performance predictor, C prime of A, is a function which predicts the score of the architecture A without the need of actually doing the full training P. And the motivation of using a so-called performance predictor is based on the fact that C prime needs less time to evaluate than CA. Also, ideally, C prime of A, so the predicted performance, is ideally highly correlated with the actual ground truth validation performance of the validation accuracy of the architecture. So, we talked about what a performance predictor now is. Let's talk about the actual methods we want to use. So, surrogate-based methods predict the performance of an architecture before training them fully. We can combine these different surrogate-based methods with different search approaches in order to drive the search and fasten it and making it more efficient. The overall components of a performance predictor are based on three different parts. The first part is the actual data set to train the prediction method on. Here the data set is the architecture as well as the validation accuracy. So the architecture A from the search space and the validation accuracy, the ground truth validation accuracy C of A, for capital N different neural networks, which can also be the learning curve extrapolation, for example. So instead of using the fully evaluated neural networks or the fully trained neural networks, so the validation accuracy after fully training, we can also use learning curve extrapolation. So looking at different epochs. So having now the data set, we need any kind of prediction method for the target, which can be a multi-layer perceptron, a random forest, an XGBoost. And we need an architecture encoding, which is the input to the prediction method. And the output to the prediction method is then the cost. The cost here is the validation accuracy, so the predicted validation accuracy. So we train our prediction method to predict the actual validation accuracy or the learning curve extrapolation, if we go for learning curve extrapolation. In order to actually do the prediction method, we can select from various regression methods. So we talk here about a regression because our targets are mostly accuracy performances. So therefore we can use various regression methods from the machine learning, deep learning area, using graph neural networks, for example, given the fact where you have graph designs and graph encodings. We can use a random forest, we can use an XGBoost, and we can use MLP, all various regression methods. And most popular in us are graph neural networks, given the inherently given graph representation of our networks. So now we will talk about the encoding. So if we decide for a performance prediction method, for example, an MLP, we need to somehow input the architecture into that MLP using any kind of encoding. If we talk about, for example, cell-based search spaces, we can look at our neural network cells being small directed acyclic graphs. These graphs can be represented as an adjacency matrix. This adjacency matrix can then be just like flattened into a vector representation and inputted into an MLP or a random forest. So we have a vector representation which we can easily use with any kind of machine learning prediction method. The architecture encoding are based on the fact that we want to circumvent the discrete graph representations using different kinds of encoding, allowing two different search approaches with performance prediction methods. A very popular encoding are also path-based encoding. So we look at all possible paths of a small cell, for example, from the input to the output within the search space. And then we just like index those, have a large one-hot encoding, and just say these paths are within the network and these are not. So we would have a binary encoding of ones and zeros. The summary of this part is based on the fact that we want to evaluate architectures for the actual search. However, evaluating them from scratch is prohibitively expensive. So therefore, performance predictors can be used to provide a fast technique for estimating the architecture quality. And the predictor contains three different components: the data set of evaluated architectures, an architecture encoding, as well as the prediction method. And the architecture encoding is kind of the key design choices. What kind of encoding and how can we encode different networks? We can use adjacency matrices, which though have issues if we scale to larger networks, since adjacency matrix scales quadratically with the size of the architectures. We can use path encodings. They even scale exponentially with the size of search spaces. And different graph encodings using the directed acyclic graph representation, which can also face issues when we talk about very large networks. So all these key design choices are important to, all these key questions are important to choose which kind of design and encoding dialect you want to use. So each of those encodings can have different trade-offs. I hope you learned now a lot about performance estimation strategies, and happy to see you in the next video.